and the laden flows. Let's welcome Professor Liang from Ocean University.
Thanks, Chairman, and good morning, ladies and gentlemen. It's my honor to introduce our job. In fact, this job not finished yet fully, but I just introduced some progress nowadays. And my topic is development and application of a two-phase mixture model for segment London flows. We focused on the deep sea Mandarin, the trading problems. So we chose this topic. And the main program is made by Bo Yang. He is my PhD student. And the third author is my colleagues. My report includes the four parts. First, I will introduce the background. People start to pay much attention about deep sea Mandarin, and we know here deep sea Mandarin is referred to three types of marine Mandarin deposits on the sea floor. They are the manganese nodules and the ferromanganese crusted and the sea floor massive sunbite deposits. So this machines and the procedure to get the deep sea mineral, we can see some machines to disturb the sea bed and the hydraulic pumping to the platform and release the sediments there. So from this picture, we know nodules harvesting activities and tailings discharge will make a lot of sediment problems and in the water and cause invisible impacts on the marine environment and the marine biodiversity. This picture, this animation is from MIT. We can see there are a lot of the deep sea minerals on the back, and if we disturb the seabed and much sediment clouds occurs. So we focus on this problem, but this problem is a serious problem because deep sea Mandarin is very important for our country, even for the world. But now it's far from distant from the commercial scale use deep sea Mandarin. It's a serious problem we have to solve this. But to do physical experiments is difficult for this problem. We chose numerical modeling. But this for the numerical modeling, we need to focus on the sediment deposition and the turbulence diffusion here. And before we start to focus on problems, we need to select suitable modeling. So there are three kinds of numerical modeling available to solve such problem. And first is Lagrange model. In this model, we know that its first phase is treated as a certain number of individual particles. For HPH model, this continuous term is also treated as the individual particles. That means we need a lot of number of particles and we need a lot of computer time. Some short terms. And another one is a single phase model, and many kinds of single phase model. Here, this equation solves it's a simple model, but they neglect the effect of the dispersed phase on the continuous phases. The suspensions may exhibit the characteristic of non-Newton fluid. So this kind of model cannot solve such problems. And another one, from this course lab, I see many scientists pay much attention about this one, and many scientists study give a good result for HPH to solve such problem. And here we know even Ola model is very are very accurate, but the complex constituent equations for the average stress term, turbulent stress, and the interaction forces between the sediment and the water, we need some simplifications to do this. So, but the Ola model also needs to solve many equations. So how can we solve this problem? We think we need to combine the models. So we know the multi-phase modeling component employs a single-phase colloquial relations extended in the situation. So we need to combine the single-phase model and the Ola model. Our job want to get the three objectives. So we need to develop a CFD-based two-phase mixed model for turbulence diffusions and depositions of sediment landed flows. And then we need to understand the deposition and diffusion characteristics of disturbed sediment and the different hydrodynamic conditions. And the third purpose to understand the interaction between the heat-heating system and the seabed to estimate and minimize seabed disturbance. If we want to develop a numeric model, the important thing to verify the model. And here, I want to introduce the series about the two-phase mixed model. And the two-phase mixed model first proposed by Wallis and then further developed by Essay and inspired by the Butterworth job is published a paper in the POF last year, and he further implemented into the SPH method to simulate turbulent sediment report. But inspired by him, we want to explore the two-phase mixed model under architecture, SPH architecture into CFD architecture. So that's because we think the CFD, the two-phase mixed model CFD may be the higher computational efficiency compared with the SPH model. And we focus on the deep sea measuring problems. So we chose the three commonly used examples. And this one is the second particle cloud, Butterworth is reported last year. And this one also experimented by Butterworth in Singapore. And this one another case. All the three cases problem similar environmental problems faced by the deep water measuring. Here is the numerical model. In the third model, Ola model, we need to solve for the continuity and the momentum equations for each case, each phases. Here is the water and the sediment. We need to solve many equations, but the primary equation for the two-phase mixed model is obtained by summing over all the phases in the Ola model according to the following definition mixture. Here, details we can find. I didn't introduce here. And we know the phase pressure are often taken to be equal Pi to Pi here. We need to have such assumptions. And here, S and F represent this first phase and the continuous phase. But the equation, if we want to combine the Ola equation to here, we need to solve the three terms. The three terms is very important. How can we give accuracy by definition? First, we go to these terms. And we know these terms is the diffusion stress due to the phase slip. If the two-phase model, we can account for this, but for our mixture model, we need to account for the phase slip diffusion, and this is the equation. And the USM and UFM is the diffusion velocity of each phase from this figure. We know the mixture velocity and the sediment velocity and the fluid velocity. We can get the three terms. And it's difficult to get this, so we change to another formulation. We can use this USF equals to US minus UF, so we can get the velocity of dispersed phase relative to velocity of a continuous phase. Usually it's easier to get the continuous phase velocity, and then we can get the diffusion velocity of the dispersed phase is the equation 14. And so we get USM, and we can use USM, and we can use USM here. It's the equation 9. And the next step, we need to get the USF parameter, the velocity. And how to get the USF? We separate it to the non-cohesive segment and the cohesive segment. For first, for standard particle, a common form for the relative velocity, we can use this equation. This equation we can know. Usually we use single phase. We just focus on this. This one means static velocity. But this is the two-phase mixture model. We need to think about the acceleration of the mixture. So we use this equation. And the drag coefficient here, we use the equation 16. And the RES is the particle Reynolds number. And when the suspended sediment concentration is very high, you know, if sediment is very high and the turbulence damping function cannot be neglected, so we use this equation to get the velocity. And for the clay particles is quite different from the sand particles. It's the proliferation is very important. We have to account for this. So we, except for the sediment density and the particles, we need to account for the flow size. So we chose this formulation to calculate the velocity. And here we can choose make it different. We can choose make different the velocity formulation. But here we will to compare with the Bernoulli's dot. He uses this, so we use it to keep the same setting parameters. And this equation we know we focused on this. We already done this definition we call DM. It's diffusion stress. But the next step we need to get the formula to parameters. And the formula to parameters is viscous stress and turbulence stress. It's usually defined equation 22 and 23. And but we know for the viscous stress, we have to it's almost related with the sediment concentration. So for the different sediment concentration range, we need to choose different viscosity model to calculate this viscous stress. And for the turbulence stress are defined as equation 23. And you know, in my case presentation, I account for the sediment damping function in the bottom in the KH model and the bottom as the bottom boundary. But that is the single phase model. Here we also to introduce the Boise terms in the KH model. Many persons who start off here didn't introduce details. We use this to account for the gradient of density. And this is the K omega model parameters. And how can we solve the sediment and water? we choose usually we choose the VOF method to simulate the diffusion and sedimentation processes of sediment in water with this equation, and we adopt the OpenFOAM 2006 to solve as a calculator to solve these problems. Here it's different from the battery stop. Battery stop is adopt the SPH method. And to verify the model, we need to choose some typical experiments for deep sea measuring. The first is we can see the deep sea measuring is the Tading discharge. To simulate the Tading discharge, we chose the setting of particle cloud. Here is the particle cloud. Here is the initial, and this waves and this heights. And we can release the particle around the cloud, and we record the deposition, vertical deposition, and the waves. We don't just compare with the Bertwick's SPH model. We also compare with the Shi. It's students of I think Professor Yu Xiping, and another guy is last year Funky SPH model, and we use the same parameters as the former 3 SPH experiment, the case parameters, and this is the wax, and different is the diameter. From we can see the diameter is quite different, so we can get the quite different velocity, secondary velocity. But the secondary velocity is very important to simulate this accurately. And suspension viscosity model, this model we chose to calculate the viscous coefficient and the relative velocity. We can use this to get this give a brief description of the experiment. And now we give the after 1 second we give the picture of the sediment concentration. This is the SPH model. We can see the shape. This is the CFD outgrowth model. The result we can see is quite similar, but the value, the sediment value fraction distribution is also similar. This is the 1 second. To compare the detailed information, we go to the last slide. This slide, we have the 4 cases we compare. From this, we can know for case 1, this is the blue line is our job. This one is the Bertwick, and another one, the dashed lines is the fountain, and another one is the Shi. So from here, we know for the case 1, except for the 2.5 seconds, other time is almost get a good achievement, good agreement with the measurement, and we better than Bertwick, but a little the accuracy is not lower than the Shi, because we have some simplification. And another we can, for the case 3, we also similar phenomena, but for the waves of the another 2 cases, we also can find such information. The result of the CFD model is better than Funky and the Bertwick SPH model, and get the similar results as Shi result. And that's the Tading discharge. Next, we focus on the this curve of the C5. Bertwick to do such experiment in Singapore. We get the experiment stage. This experiment have this carried out in this tank, and have the betonated clay, and the water mixture is here. It's almost 30 centimeter. and the total, and the upper layer is the clear water, and the length is the 1.7 meter, and the total height of the tank is the 0.7 meter. And we keep the same parameter as the waterways. This is the experiment numerical simulation parameter setting is table 3. We use in-hand model to describe the viscosity effects, and data information I didn't introduce here. We can find this slides. This incline stands for the plate. We disturb the seabed to get the minerals from the seabed, and in the first it needs acceleration. Acceleration is 0.0282 square meter seconds, and when reaches the velocity 0.142 meter per second, and keep the constant velocity. This so we go to next slide. And how can we to do such numerical modeling? We chose arbitrary coupled mass interface method, and we use one set of method, but the mass divided into the stationary zones, and the moving zones. So stationary is the upper stationary zones and the lower stationary zones. The moving zones move with to the right, from the left to the right, with a given speed. The stationary zones remain stationary, and to ensure the accuracy of the modeling, the overlapping boundary is the ACM boundary, and the non-overlapping boundary is the warp boundary. We can see here. If this zone enter this tank, we can get the ACMI boundary. Only ACM boundary exists information and transfer between the regions only through this boundary. And the figure 12, so the procedures of ACM mass motion, and we can see from the left to the right, we can solve such problems. But the mass size of the stationary region and the moving region at the ACMI boundary is we try to keep consistent as possible. And we go to the picture simulation results, and from this picture we saw the segment concentration fraction distribution, and this experiment is SPH experiment. This is our job experiment. So from here, this is the velocity of the SPH and CFD. From the three pictures we know, this one is not clearly detected from the bed. So we can see our case not clearly, but for SPH model, it was very clear what has developed. And from the velocity of the picture, we also can find such information. And from this picture, we know this is the whole process of the plate pushing movement. We can find it's quite similar phenomena occurs, but around here, almost end of here, we can know the vortex webbing shading is similar for our case for CMB model and experiment, but for SPH model, it's a little earlier, the shading time and the shading position a little earlier. So from this case, maybe we can know if we keep the same parameter, the CMB model have a little better than SPHD method. This one, I forgot to introduce. This one is the result at the 9 seconds after the plate motion. And we need to get the appropriate mass resolution. So we test the resolution, this like mass 1, mass 2, and make a mistake, and from 1 to 3, 4, and the mass the resolution is 0.25 millimeter until to the 0.75 millimeter. And we compare the full mass grade resolution. From this picture, we can get the concentration. We know for the if lower resolution, we cannot see the clearly what has, but if we increase the resolution, we can see more clear what has developed. But if we compare the mass 3 and mass 4, it's almost similar. We also can find the similar for vorticity for the mass 3 and the mass 4. If we focus on the force, the external force, we can find almost similar within the acceleration state after reach the uniform constant velocity. We also similar, but after 8 seconds, we can quite different for the mass 1 and the mass 2, and mass 3 and mass 4 is quite similar. But mass 3 is the resolution is lower. So we need to choose mass 3 as the benchmark method. And we get the boundary.
Professor Liang, you stop almost your time.
Okay.
Yeah, so I don't know how many slides you have.
I will give a brief introduction for the last several slides.
We may not have time for questions. So, yeah.
So I neglect the last one case and neglect the conclusions. So thank you for your attention.
Okay, thank you, Professor Liang. So maybe we have the time for one question from the audience.
Professor Liang, I think this is very good work. I don't have a question, but I have a comment. Can you go to the slides with the comparison between the experiment and numerical results for those animations? The one with the video.
The video?
Yeah. Earlier one.
This one?
Okay, yes. If you look at the experiment, and then you will see actually the particle is more difficult to settle down in the later stage. So I was thinking maybe in your simulation, if you use a smaller settling velocity corresponding to the smaller particle size, maybe you will get better agreements. But I'm not sure whether this is a case, but just look at the video. And after this pass by, those clouds stay a long time, but in your numerical simulation, on the later side, it's quickly settled down and almost no motion.
Yes. The settling velocity is very important. So we just choose the same velocity as the SPH model as the first phase. So we have some formulations to calculate this calculation about this.
Yeah, but maybe you can take a try. Another one is that can cause the difference between those experiment and the simulation would be your turbulence, the AD viscosity used in the model, and as well as velocity. I'm not sure whether there's any measurement or comparison of the velocity after those plates pass by. There's some residual. Now we just compare those vortex. Yeah, but this is just comment.
Thank you.
Okay, thank you very much. So if Okay. So if
May I?
there are more questions from audience, I encourage you to talk to Professor Liang after this session.
Okay.
Okay. Thank you, Professor Liang.
Okay. Thank you.
Okay. So our next speaker is Dr. Xuyang Niu from Dalian